Now, let's talk about facilitated diffusion right here. Remember that when we're talking about facilitated diffusion, we're having to do with transmembrane proteins or these carriers, right? And the reason for that is we're having to do with ions, right? So a little bit bigger molecules, or sometimes a little bit bigger molecules, but they also have these charges, right? And this is very important because the phospholipid bilayer does not allow for these charges to come inside, right? So in simple diffusion, you do not have ions, but here we do have ions, and they can come through via these carriers. So let's do this task here. A cell contains ions with the following concentration among others. The corresponding extracellular ions concentration are also provided. The temperature is 310 Kelvin. Assume that membrane potential is minus 65 millivolts and the cell membrane is permeable to the ions listed below. So here we have some ions, of course, and the pH here is H plus ions because pH is simply an expression of how many H pluses we have in a solution, or hydrons in the solution. And here we have the concentration of these ions in the intracellular and extracellular fluids. So the first thing they ask you to do is calculate for each ion the equilibrium potential, and then the electrochemical potential difference, and then the driving forces for each of the ions. So we begin by calculating the equilibrium potential for each of the ions by utilizing Nernst equation. So this is the Nernst equation. R, the gas constant, is given to this. The temperature is 310 Kelvin. The ion valence is specific for each ion. For example, for sodium here, it's +1. For potassium, it's +1. For chlorides, it's -1, so on and so forth. Here we have Faraday's constant. And now we insert our values into the formula. Of course, this is the concentration of inside the fluid and outside the fluid. For example, for sodium here, it is 12 millimoles intracellular and extracellular 155 millimoles. We do this for each one, and here are the answers. But for pH, or for H plus ion, we don't have the concentration given. We have the pH given. But it is actually quite easy to convert this because pH is simply defined as the negative logarithm of the concentration of H pluses. So you can utilize this equation to calculate the amount of hydrons we have in the intracellular and extracellular fluid. And then you can insert this in the Nernst equation to give us the final outcome, or the final equilibrium potential for hydrons. And now let's calculate the electrochemical potential difference between the inside and outside of the membrane for each of the ions, which has a specific valence. We utilize this formula. We already have some constants giving. The membrane potential is given in the task to minus 65 millivolts. And of course, the concentration intracellular and extracellular fluid is given. So now you can just put all these in and calculate. So here are the results given. Okay. So this is one of them, this is one of them, this is one of them, so on and so forth. You get the idea. Now let's calculate the driving force, right? Just so you guys remember what driving force is, well, driving force is also known as the electrochemical gradient, or the potential for net ion transport. So this is the difference between the membrane potential and the equilibrium potential for a given ion. So this indicates the resulting force that drives ions either out or into the cell. So I've calculated for each of the ions here, and now they ask you which ion is the closest to equilibrium and which one is the furthest from equilibrium. So we can of course utilize the driving forces to look at that. So based on the given values, potassium here ion is closest to equilibrium. It's close to 0. And then calcium is the furthest from equilibrium it is the furthest from 0, as you guys see. By the way, just so you guys understand here, if the driving force is positive, for example, for potassium here, well, that of course means that the membrane potential, so the membrane potential is higher than the equilibrium potential. And likewise, if the driving force is negative, for example, for sodium here, it means the equilibrium potential is greater than the membrane potential. Now let's do this one right here. In which direction does each ion move passively? Here, I want you to remember that it has to do actually if it's cation or anions. You cannot simply look at driving forces and just make a decision like that. It's not that easy. You can utilize this table. So for example, sodium here is a cation, and also the driving force is negative, so it's influx. So sodium enters the cell. If you look at, for example, potassium, well, that is also a cation, but now the driving force is positive, so it's efflux, so it exits the cell. Then if you look at something like an anion, like chloride, which also has a negative driving force, so it is efflux, right? It's an anion, it's negative, it's efflux, so it exits the cell. However, if you don't have this table here, I want you to remember a thing here. Remember that let's just take an example here. Let's take sodium as an example. Let's take potassium as an example here. So suppose we have potassium, look at the driving force, it's positive. So the positive net driving force, which is the direction of net current flow, positive charge, is outwards. And K plus is actually also outwards. So here for potassium, it exits the cell. Right? And you can look at that because you can look at the relation between Vm and Ex. Or give me a second here. So the membrane potential, right, for potassium is given as minus 0.065 volts, and the equilibrium potential is given as, for potassium, is given as minus 0.084. So this actually means that it will go down like this. It will go down like this, right? So we're at the membrane potential, right? And it will equalize by going at the equilibrium potential. So it will exit this cell. Okay? And similarly, you can do it for all of the other ones, but I don't have time for it right now. Now they ask you what could happen with the released energy. Well, the released energy from ion transport can be used to perform various cellular processes. For example, just to give you guys one example here, secondary active transport, right? Now they ask you how much energy is required to transport 1 mole of sodium plus out of the cell. So this is the same amount of energy with in transport or transporting inside. So this must be this right here, but just now it's positive, it's not negative.